Now let's look at the maximum principle. This is a set of necessary conditions that hold only on optimal paths. It is the main tool used in dynamic programming or optimal control problems. Now let us look at the general form of the dynamic optimization problem with a finite time horizon and a free endpoint. What does a free endpoint mean? The meaning of this term will become clear as we move on. So you want to maximize J, or functional, between the lower limit of 0, upper limit of capital T, right, integral, f of x of t, y of t, and t dt, right? So your function will include an x, which is a function of t, y, a function of t, and t itself, explicitly, subject to some differential equation governing x. So x dot is equal to some function g of x of t, y of t, and t. And then you have a boundary condition, x of 0 is equal to x naught, which is greater than 0, and this is given. So look at the upper limit of the integral, this thing. Capital T is unspecified, or in the language of optimal control, it is unrestricted. In other words, it is free to be chosen optimally, and the quantity x of t then becomes an optimal quantity. This is what is meant when we say free endpoint, and then we shall encounter these terms again in other lectures. J is the functional, x of t is the state variable. This is very important. Y of t is the control variable. It is directly chosen or controlled. You must be able to identify the state and the control variable in any dynamic optimization problem. Within the context of our profit maximization example, the state variable x of t would be the amount of capital held by the firm. The control variable y of t would be the amount of investment. X of capital T itself could be equal to some given value, in which case it would be an equality, x of capital T is equal to x naught, and then it becomes a fixed endpoint, or its value would depend on the nature of T, capital T. Capital T could be freely chosen, as we have already seen, or it could be infinity. And the nature of capital T determines the solution to the problem. The solution of the problem itself is the path of the control variable y of t. Once y of t is chosen or specified, the path of the state variable x of t is automatically determined through the differential equation governing the state variable. Now assume that the control variable is continuous in time, as is the state variable. Then the necessary conditions that constitute the maximum principle are stated in terms of the Hamiltonian function. This is a bit like the Lagrangian function. So the Hamiltonian function h, which would be a function of x of t, y of t, lambda of t and t, is equal to f of xt, yt, and t, plus lambda t multiplied by g of xt, yt, and t. Lambda t is the co-state variable. It is like, but not exactly the same as the Lagrange multiplier, but it has a very similar interpretation. Now, what are the necessary conditions? If you want to see a derivation of the necessary conditions, please consult the textbook. So the first condition is del h by del y is equal to 0. And the solution to this equation gives the control variable y of t, which maximizes the Hamiltonian. Then you have two important differential equations. You have a lambda dot, which is equal to minus del h by del x, and x dot, which is equal to g of xt, yt, and t. X dot is actually one of the restrictions of the problem, of the maximization problem. See, this is subject to x dot is equal to g of xt, yt, and t, and this forms one of the differential equations that need to be solved. So you have this pair, right? This is the pair or system of differential equations which need to be solved, possibly simultaneously, and the solutions yield the paths of the state and co-state variables. The state variable is x of t, and the co-state variable is lambda of t. The boundary conditions used to solve the system of differential equations are x of 0 is equal to x naught, usually of some positive value, and lambda of t is equal to 0. This last condition is called the transversality condition. And while these are necessary conditions, there are also sufficient conditions, and they exist as well, but they are beyond the scope of this course, so we will not discuss them. Let's look at an example. So you want to maximize between the lower limit of 0 and the upper limit of 1, the functional x minus y squared dt, subject to x dot is equal to y and x of 0 is equal to 2. This is our initial condition. It is understood that x and y are all functions of t. Identify the state and the control variables. In this particular case, our control variable is y and our state variable is x. And here we have a lambda, which is our co-state variable. Right, so you form the Hamiltonian x minus y squared plus lambda y, apply the maximum principle or the first order conditions. So we have del h by del y is equal to minus 2y, right? So if you differentiate h with respect to y, you get minus 2y plus lambda, and you have to set it equal to 0. And from here, we get y is equal to lambda by 2. i.e. y of t is equal to lambda of t by 2. The differential equations for the co-state and state variables. So the co-state variable has differential equation lambda dot is equal to minus del h by del x. Now, del h by del x is equal to 1, minus del h by del x is equal to minus 1. And we have from the restrictions, subject to conditions, x dot is equal to y. But since y is already equal to lambda by 2, we can write x dot is equal to y, which is equal to lambda by 2. We have the boundary conditions. X of 0 is equal to 2 and lambda of 1 is equal to 0. Right? So we are making use of the free endpoint condition. Lambda of capital T is equal to 0. So 1, right, is your capital T. So the transversality condition requires us to set lambda of 1 is equal to 0. Now, look at the pair of differential equations. You have lambda dot is equal to minus 1 and x dot is equal to lambda by 2. These differential equations are simple enough and we can solve them separately, one at a time. So lambda dot is equal to minus 1. This implies that if you integrate both sides, you get integral d lambda is equal to minus integral dt, which implies that lambda of t would be equal to c1 minus t. But we have the transversality condition, lambda of 1 is equal to 0, which implies c1 minus 1 is equal to 0, which means that c1 is equal to 1, so lambda of t is equal to 1 minus t. Now, y of t is equal to lambda of t by 2, which means that y of t is equal to 1 minus t by 2, so we have solved for the control variable. When t is equal to 0, y of t is equal to half, which is the solution of the control variable when t is equal to 0. We also have x dot is equal to 1 minus t by 2. So again, you can integrate both sides. So when you integrate both sides, you have on the left-hand side, you have dx by dt, right? You have dx is equal to 1 minus t by 2 dt. Then you integrate, you have integral of dx is equal to half 1 minus t dt. So this means that x of t is equal to half into t minus t squared by 2 plus c by 2. So x of t is equal to t by 2 minus t squared by 4 plus c2. But x of 0 is equal to 2, which means that c2 is equal to 2, right? When you plug in t is equal to 0, you get 0 minus 0 plus c2 equal to 2, which is one of the conditions, x of 0 is equal to 2. So we have x of t is equal to t by 2 minus t squared by 4 plus 2, which is the solution path of the state variable. So this is the solution to a relatively simple optimal control or dynamic programming problem.